High in the Rocky Mountains, water trickles from the earth and slowly flows downhill. This trickle of water marks the beginning of the Colorado River, a young, powerful stream that has shaped much of the western landscape. Later, we will compare the Colorado to a much older river, the Mississippi. From its modest origin in Colorado's Rocky Mountains, the river flows across Utah into Lake Powell, through the Grand Canyon to Lake Mead, then to Hoover Dam in Nevada, continuing south, forming the border between Arizona and California, into Mexico, where its 1,700-kilometer journey finally ends in the Gulf of California. A close look at the water reveals silt, sand, and other debris. This sediment material, eroded from the land over which the river passes, forms the suspended load of the stream. The steep gradient or slope of the land causes the water to flow faster. As stream velocity increases, the water picks up rock particles, which abrade and polish the rocks over which the stream passes. Here, where the gradient is less steep, the water velocity slows. The Colorado River now winds through the valleys it has carved into the Rocky Mountains, taking the course of least resistance. Because the stream gradient is constantly changing, so does the stream's velocity. Here, the river current is slow. Elsewhere, it is a faster, powerful, more narrow stream. The strong current produces turbulent flow, enabling the water to move pebbles, cobbles, and even boulders. These heavier rocks are part of the solid material carried by the river called bedload. Such large sediments are transported along the stream bed in places where currents are very strong. But where the gradient is reduced, current velocity slows, and the river is wider and deeper. Here, the Colorado and its ever-increasing number of tributaries gather still more sediment to be transported and eventually deposited at other locations downstream. Many small creeks originate in the high mountains and join the Colorado River on its long journey to the sea, with the addition of these tributaries as it flows downslope. Leaving the mountains, the Colorado flows into a valley. The river is swollen from rain and muddy from its increased suspended load of sediment. Because volume and velocity have increased, the river can carry a heavier load during times of flooding. Downstream, we see steep canyon walls. These massive erosional landforms are evidence of vigorous downward erosion. Over millions of years, the river has scoured the land, removing rock and soil and carrying it away as sediment. But as the volume and velocity of the river decrease, some of this sediment is deposited to form depositional landforms such as sandbars. Sandbars consist of many layers of sediment. The layers are not of uniform thickness, for each layer represents a specific interval of deposition. How much sediment does the Colorado River carry? Measurements by the United States Geological Survey made at field stations along the river, including this station at the Colorado-Utah border, determine current flow and sediment load. A current meter is lowered to a specified depth. Spinning cones atop the weight produce clicks. The more frequent the clicks, the greater the current velocity. 8 measurements are taken across the river. The number of cubic meters of water flowing out of the state of Colorado is then calculated. On this day, 77 cubic meters of water pass this station each second. But during a spring flood, the volume may rise to as much as 1,050 cubic meters per second. Now, a sediment sampler is submerged at selected points across the river. The sample collected will reveal the various sizes of sediment carried in the suspension. Much of the river's load consists of sand, silt, and clay suspended in the water. But larger particles are bounced along the stream bed in a process called saltation. Still larger rocks are pushed or dragged along the bottom, The amount of sediment in each sample is measured to determine the sediment load of the river. Today's samples indicate that 1,100 tons of sediment pass this point every 24 hours. At flood stage, sediment load may rise to as much as 65,000 tons per day. As the Colorado River flows across the state of Utah, we see spectacular evidence of the river's ability to shape the landscape. Running water has cut through ancient layers of rock, producing scenic monuments to erosion. But the river has also built up the land. Sandbars have formed as sediment was deposited where the river meanders, and stream velocity was reduced. This plateau reveals the beginning of a series of canyons carved by the swift waters of the Colorado River. Here, stream erosion has exposed a great slice of Earth history, for these rocks are more than 200 million years old. But when compared to Earth's 4.5 billion year history, they are relatively young. The walls of the canyons have been widened by lateral erosion. Rains loosen rock and soil, causing them to move downslope in response to gravity. During heavy rains, water runs off the surface before it can be absorbed by the thirsty soil. Excessive runoff may create flash floods, as shown in these rare shots. Sheets of water sweep over the land, removing sediment from areas of sparse vegetation. Here, as the sheet of water spreads, it acts as sheet wash, carrying away loose debris that lies in its path. Eventually, some of the water is funneled into stream-cut gullies that may join a tributary which will flow into the canyon. The Green River is a major tributary of the Colorado. Where the two rivers join, we see the sediment load of the muddy Green River on the right, entering the Colorado on the left. The Green River collects sediment from an area of hundreds of square kilometers, adding it to the load of the Colorado. In addition to downward and lateral erosion, stream channels also undergo headward erosion. This lengthens the stream and may cause one stream to join another, capturing its waters. This is called stream piracy. In addition to nature, human activities have also altered the character of the Colorado River. In southern Utah, the river has been dammed to form an artificially created lake, Lake Powell. This huge body of water fills the canyons and stretches almost 250 kilometers through Utah. The lake serves as a reservoir to store precious water that flows out of the mountains. Lake Powell reaches its widest point near the border of Utah and Arizona, where Glen Canyon Dam interrupts the river's seaward journey. But some river water flows through the dam and continues downstream. A satellite view reveals the extensive network of canyons carved out of the Colorado Plateau, further evidence of the Colorado's ability to erode. The Grand Canyon of the Colorado River is one of the Earth's most spectacular natural wonders. It is also the classic example of erosion by running water and a scenic area of awesome grandeur. For more than 8 million years, the Colorado River has been carving a huge canyon that is now some 350 kilometers long, approximately 30 kilometers wide, and about 1,700 meters deep. The younger rocks in the upper part of the canyon wall lie relatively flat, but deeper within the canyon, along the river's bank, The rocks are severely deformed and almost 2 billion years old. Geologists compare the rock layers in the canyon walls to rocky pages in a giant earthen history book. Nowhere else on Earth is there such a comprehensive record of this part of Earth history. The river is interrupted again near the southern end of the Grand Canyon, where another dam forms Lake Mead. At this point, the river slows down and deposits its load. Upstream, sediment discolors the water, but downstream, the water is clear. Each day, approximately 80,000 tons of sediment are deposited on the bottom of the lake. At this rate, Lake Mead will be filled with sediment by the end of the 21st century. Because many lakes silt up and become filled with stream-borne sediment, geologists consider lakes to be temporary features of the landscape. Lake Mead forms behind Hoover Dam. This monstrous dam makes it possible to regulate the output of the Colorado River, thus preventing flooding further south. Hoover Dam is a great asset to this region. Each year, its 17 generators produce 6 billion kilowatt hours of electricity, providing power for energy-hungry metropolitan areas in Arizona, Nevada, and Southern California. People also depend upon this river for drinking water. Below Hoover Dam, water is drawn off by 3 huge pipes burrowed through the mountains. The intake station pumps enormous quantities of water to large cities, such as Las Vegas and Los Angeles. This life-supporting supply of water has helped Los Angeles reach its current size. Rivers are lifelines that have enabled civilization to build and thrive in the very arid regions of the West. Thanks to water supplied by the Colorado River and controlled by Hoover Dam, farmers in Southern California and Arizona have turned the dry desert into rich, productive farmland. Irrigation, fertile soil developed from earlier deposited river sediment, and an almost year-round growing season make Imperial Valley one of the largest and most productive farming areas of the Southwest. The water that has not remained stored in lakes, used for irrigation, or siphoned away to desert cities flows southward into Mexico and the Gulf of California. In this exaggerated profile, we see that the Colorado River descends 3,000 meters to reach sea level. Along its journey, it passes through Rocky Mountain valleys, Lake Powell, the Grand Canyon, Lake Mead, and into Mexico. In this infrared satellite image, the red and yellow areas at the top of the screen show the fertile Imperial Valley. At the lower right is the large delta, formed by sediment deposited at the mouth of the Colorado River, where it drains into the Gulf of California. It is here that the long journey of the Colorado River is finally completed. The Colorado River drains approximately 630,000 square kilometers of the southwestern United States. But in contrast to the young, swift-flowing Colorado River, the slow-moving waters of the much older Mississippi River drain an area roughly 5 times as large, approximately 41% of the surface of the United States. The mighty Mississippi is a river that flows slowly, almost sluggishly, across the lower part of the United States, where the surface of the land is nearly level. From here, north of St. Louis, Missouri, we will follow this river on its long, winding journey to the Gulf of Mexico. We will encounter little turbulent flow because the Mississippi has eroded the surrounding land to the extent that the stream gradient is almost flat. The flatlands surrounding the riverbanks consist of fertile soils that are excellent for seasonal crops in this northern climate. These soybeans are growing on a fertile floodplain produced when the Mississippi overflowed its banks. Like many of the world's great rivers, the Mississippi is an important route of commerce. Tugboats push multi-coupled barges up and down the river, carrying a variety of materials and enabling Midwestern states to have access to the waterways of the world. St. Louis has been called the gateway to the West because it is an important inland port. Here, the river meets a web of railroads and highways that leads to all parts of the country. St. Louis has become a major city because of its prime location on the Mississippi River. On a special track beneath St. Louis's major highway, a rail car moves over the river. It enables United States Geological Survey geologists to study the Mississippi, using the same methods employed along the Colorado River. Measurements are taken that provide information useful in flood control in the vast Mississippi River Valley. Studies of sediment loads enable engineers to determine where navigation hazards might occur from excessive sediment deposits on the riverbed. In places, the river flows over land that is so flat that the path of the river will stray. This produces smooth, loop-like curves called meanders. When a stream begins to meander, it cuts into its banks, forming meander loops, which gradually erode laterally as they migrate downstream. During times of flooding, water covers this nearly horizontal surface. We see Mississippi River meanders in this infrared satellite image. And now, at flood stage, the extensive blue reveals the amount of land that the river claims as its floodplain. In the spring, there may be periodic flooding along the Mississippi. Farmland is covered, topsoil washed away, and property destroyed. The river that has left its surrounding land so fertile can also be ruthlessly destructive. And because the land is flat, dams are of little use in controlling these floods. After floodwaters recede, the stream-cut meanders are often wider than they were before. And when the loop-like meander nears a full circle, an oxbow is formed. The stream flows through the meander while side-cutting its outer bank. The lower end of the meander erodes headward, and eventually a newer, shorter channel is cut. In time, the oxbow is cut off, forming an oxbow lake. Cut-off meanders and oxbow lakes are common features along certain older rivers. Along the river banks, flood-borne sediments may build natural levees. This cross-section reveals how, during flood stage, natural levees may form when a stream flows onto the floodplain. The largest amount of sediment is laid down along the banks of the channel and tends to build up a ridge or natural embankment. Sediment also accumulates in the middle of the stream, making the river increasingly shallow for navigation. Sediment-choked channels must be dredged to keep the river open to transportation. In this operation, a massive cutting head is lowered to the river bottom. The rotating head cuts and scrapes sediment from the riverbed and sucks it away through a pipe to be deposited along the shore. If the lower parts of the Mississippi were not dredged, the river would totally close itself off to shipping and would also create serious flood hazards. The Mississippi River passes New Orleans before reaching the Gulf of Mexico. New Orleans is the mecca of most transportation along the river. Here, river barges meet with ocean-going freighters to ship and receive products and raw materials from around the world. In this satellite image, we see the Mississippi entering the Gulf of Mexico, where its velocity and ability to carry sediments diminish rapidly. The river drops its load, and the accumulating sediments form a delta. The light-colored area on the right shows sediment deposited in the sea. As more sediment is added, the delta grows progressively farther into the sea. As the river approaches the Gulf, we can see that the main channel divides into many new channels or distributaries which form on the delta surface. Between the distributaries, shallow embayments become filled with fine-grained sediment to to eventually become saltwater marshes. Rivers have affected the earth and its inhabitants for billions of years. But the path of a river today may not be its path tomorrow. The face of our planet undergoes constant change, and many of these changes have been caused by running water, a major geologic process that will continue to operate for millions of years to come.